Hello friends. So in the previous session we have done around 3 numericals regarding the losses associated with the transformer. So let's continue with these numericals, because these numericals are very important in understanding the losses of the transformer, like the hysteresis loss and eddy current loss, specifically core loss. Because these core loss problems are usually asked in competitive exams because these are easily solved. There is not much amount of calculation required. So these are basically ratios that you have to solve. And for objective type questions, these are a good area to ask the questions. Okay, so today let's do 3 or 4 questions also, and in the next session also we will be doing some numerical, so that we can cover almost all the variety of problems. Okay, I still recommend you always go through more problems when you are preparing for exams like GATE. Okay, understanding the theory is well and good, but the application of this theory is usually in numericals. You should do maximum problems from various books, so that you will have a good grip on the subject. Okay, so with that, let us start today's numerical. That is a 50 Hz single phase transformer. 50 Hz single phase transformer has equal hysteresis and eddy current loss at rated excitation. Okay, so what it meaning is that, for example, the rated excitation is say V1 voltage. Okay, you are applying V1 voltage and 50 Hz. So at that time, the hysteresis loss and eddy current loss are having the same value. For example, 100 watts means both are having 100 watts. So if it is operated at 90% of excitation and 50 Hz, okay, so afterwards you are giving 0.9 into V1 and 50 Hz, they are asking what is the percentage reduction in the iron loss. Naturally, because the voltage has reduced, the iron loss also will reduce. But the thing is, what we have to find, which case this problem comes in. Okay, you can clearly see for the first case, the V1 by F ratio will be V1 by 50. And for the second case, the V by F ratio will be 0.9 V1 by 50. So clearly here V by F ratio is not constant, right? V by ratio is not constant, because in the first case it is V1 by 50, in the second case it is 0.9 V1 by 50. Naturally these ratios are not same. So this is not constant. That means this is coming under case 2 of the problem. Okay, so this entire problem will come at case 2. Now let's see what other information has given. They have given that for the first part of the problem, that is when you are applying V1 and F. Okay, so when you are applying V1 and 50 Hz to the transformer, they have told that the hysteresis loss is equal to the eddy current loss. Okay, hysteresis loss is equal to the eddy current. That means the total iron loss of the transformer for the first case, which is V1 and 50 Hz, will be equal to WH1 plus WE1, right? But because WH1 and WE1 are exactly the same value, so that means this we can write this as WH1 is equal to WE1 is equal to WI1 by 2, right? Because this you can write it as WH1, okay, or you can write it as WE1, 2 times WH1 or 2 times WE1. So just by doing a little bit of calculation, you can find this result here. Okay, so this result is important. Okay, so now you have to find if it is operated at 90% excitation and 50 Hz. Okay, that means what they are telling is that now you are operating it at 9.9 V1 and 50 Hz excitation. They are asking you to find what is WI2. Okay, or you are asked to find the percentage reduction in the iron losses. Okay, so basically you have to find the value of WE2. So this value will be equal to WH2 plus WE2. Right, WI2 will be WH2 plus W. So this is coming in case 2 of the numericals. So the hysteresis loss in case 2 is proportional to V raised to 1.6 into F power minus 0.6, right? So I can write WH1 will be proportional to V1 raised to 1.6 into 50 Hz raised to minus 0.6, right? Similarly, I can write WH2 will be proportional to V2, right? But V2 is equal to 0.9 V1, right? 90% of excitation is applied next step. So V2 is 0.9 V1. So I can write 0.9 V1 raised to 1.6, and frequency is not changing. Okay, so 50 raised to minus 0.6, right? Simple equations we have used here. So you can write this equation as WH2 divided by WH1 is equal to 0.9 V1 divided by V1 raised to 1.6 into 50 by 50 raised to minus 0.6, right? So this value will cancel off. That means I can write this WH2 will be equal to 0.85 times WH1. Okay, so if you calculate this value, you will get this result. So this is also important for us for this numerical. Now next is finding the eddy current loss, right? You need the hysteresis loss equation we have found out, and the eddy current loss also you have to find. So eddy current loss in case 2 is proportional to V square, right? So WE1 will be proportional to V1 square. That means this WE1 is proportional to V1 is, let us for the first case it is V1 square. WE2 will be proportional to V2 square, right? But V2 value is equal to 0.9 V1. So WE2 is proportional to 0.9 V1 square, right? So this also I can write it as WE2 divided by WE1 is equal to 0.9 V1 square divided by V1 square, right? So we can write 0.9 V1 square, right? The square is coming on top. So WE2 will be equal to 0.81 into WE1, right? So this is another equation which is important for the numerical. So let's continue with the numerical now. So the Wi2, that is the iron loss in the second case, okay? So the iron loss in the second case will be equal to WH2 plus WE2, right? So this WH2 value we have already found it as 0.85 WH1, right? And plus WE2 is 0.81 into WE1, right? This also we have found out. So now we know that from the first information which is given, that WH1 is nothing but equal to WE1. Now WH1 is equal to WE1. WH2 is not equal to WE2. That is not given, okay? So WH1 is equal to WE1. So that is given in the problem. It is given in the problem. So that we can substitute here so that we will get everything in terms of one particular value. So I will write it in terms of WH1. So this will be 0.85 WH1 plus 0.81. So instead of this WE1, I will put WH1. Okay. So that means Wi2 will be equal to how much? It is 1.66 into WH1. 1.66 into WH1. And what was Wi1 value equal to? You saw that Wi1 value is equal to 2 times WH1 or 2 times WE1. Okay, so that also we can write, or I can just write it like this: WH1 plus WE1. But it is given that WH1 is equal to WE1. That means Wi1 will be equal to 2 times WH1, right? So we have gotten everything in terms of WH1, so it will be easier to solve the problem. So what they have asked is the percentage reduction, right? Percentage reduction in the iron loss. So Wi2 divided by Wi1, okay, Wi2 minus Wi1 divided by Wi1 into 100, okay. So what is Wi2 value is equal to 1.66 WH1, okay, and what is Wi1 value equal to? Wi1 value is 2 times WH1 divided by Wi1. So this is 2 times WH1, okay, into 100. So this will give you the percentage reduction in terms of the original value. Okay, so this value you will find it to be around minus 17%. Okay, so this value will be minus 17%. This minus shows the value is decreasing. Okay, so the minus shows the value is decreasing. So the closest answer is answer A. So 17.3 they have got. So this answer is A. The answer for the first question is answer A. Okay. So now the next problem also is a simple problem. So the loss of 1000 watts, okay, of a given transformer are equally distributed between the hysteresis and the eddy current loss. Okay. So what they are telling is that the loss of 1000 watts, that means when Wi1 is equal to 1000 watts, okay, they are telling that this 1000 watts is equally distributed between the hysteresis loss and the eddy current loss. So WH1 will be equal to 500 watts and WE1 will be equal to 500 watts, because the 1000 watts, which is the total iron loss, is equally distributed between these two with a certain voltage and frequency. Okay, so let us assume that this condition, the voltage is V1 and F1. Okay, so this is occurring in this particular condition. So what they are telling is that now the applied voltage is half and the frequency is doubled. Okay, so what they are asking, find the iron losses in the transformer. Okay, so what they are telling is now that the V2 value is equal to applied voltage is half, right? So this was the initial voltage V1. So now you are dividing it by 2. That is the V2 value. and the frequency value is doubled. So F2 is equal to 2 times F1. Okay, and they are asking what is the iron loss. Wi2 is equal to what? Okay, so if you see the V by F ratio in this case, so V by F ratio for the first case is V1 by F1. Okay, and the V by F ratio for the second case is V2 by F2. So this is V1 divided by 2 divided by 2F1. Okay, so this value will be equal to 1 by 4. That means V by F ratio is not a constant value. V by F ratio is not a constant value. It means that this problem is coming under case 2. This problem is coming under the case 2. Okay, so the Wi2 value, that is the iron loss value, will be equal to WH2 plus WE2. H2 is the hysteresis loss and E2 is the eddy current loss. Okay, so because this is in case 2, this is coming under the case 2 of the problem, we can write the hysteresis loss will be proportional to V raised to 1.6 into F power minus 0.6, right? So from here I can write WH1 will be proportional to V1 raised to 1.6 into F1 raised to minus 0.6, right? And this WH2 value will be proportional to V2, right? V2 raised to 1.6 into F2 raised to minus 0.6, okay? But V2 is equal to V1 by 2 and F2 is equal to 2F1, okay? So this value will be equal to V1 divided by 2 raised to 1.6 into F2 is 2 times F1, right? 2 into F1 raised to minus 0.6, okay? So from this we can find that WH2 divided by WH1 will be equal to V1 divided by 2 divided by V1, okay, raised to 1.6 into 2F1 divided by F1 raised to minus 0.6, right? 2F2, this is F2 by F1, but F2 is equal to 2 into F1, right? So this will go, this will go, this will go, and this will go. So we will finally get that the WH2 value will be equal to WH1. WH1 is how many watts? WH1 is 500 watts, right? So 500 into 1 by 2 raised to 1.6 into 2 raised to minus 0.6, right? So this value, WH2 value will be, if you calculate, it will be 108.82 watts. Again I am telling, do this calculation on your own, because there is a huge chance of mistakes that you might make during these types of problems. Okay, so now let us find, for WH2 you have found it is 108.2. So it is in case 2, right? So case 2, the eddy current loss is proportional to V square, right? So that means WE1 is proportional to V1 square and WE2 is proportional to V2 square, right? So from this I can write WE2 divided by WE1, okay, will be equal to V2 by V1 the whole square, but V2 is how much? V1 by 2, right? So this will be V1 by 2 divided by V1 the whole square. That means WE2 will be equal to, WE1 is 500 watts, right? WE1 is 500, that is given in the problem. So 500 into 1 by 2 the whole square, okay? So this value will be equal to 125 watts, okay? So the eddy current loss is 125 watts and the hysteresis loss is 108.2 watts. From these two results you can write Wi2 is equal to WH2 plus WE2, hysteresis loss plus the eddy current loss. So this is 108.82 plus 125 watts, and this value will be given around 233.82 watts. 233.82 watts. So let us see which is coming closest here. So here the closest value is 235 watts. So A is 335, 235, 425 and 225. So the closest is this value B. So that is the answer, 235 watts. Okay, so the answer is B. So the answer for this problem is, answer is B. Okay, so do these problems on your own slowly. Just understand the method by looking at the video and then try these problems on your own. These are all very simple problems. Okay, it's not very difficult. Just you have to be a little bit organized in doing all this, right? That's it. Okay, so now let us do the third problem today. And with this we will conclude this session. Okay, a single phase transformer has an open circuit and gave the following results. Okay, so the transformer is in open circuit. So this clue tells us that the power absorbed by the transformer will be only used to supply the iron losses or the core losses, because I told you already, in the open circuit of the transformer, the input power to the transformer is only to supply the no load copper loss and the core losses, but the no load copper loss we usually neglect that value. So the input power to the transformer, which is only, it is only used to supply the iron losses or core losses of the transformer. So the power absorbed by the transformer is only utilized to supply the iron losses or the core losses in the open circuit condition. So what they are telling is that when 192 volt and 40 hertz is applied, the power absorbed is 391.2 watt. And when 280 volt, 288 volt and 60 hertz is supplied, then the core losses are 73.2 watts. What they are telling is that if the Steinmetz constant X is equal to 1.6, we have to find the eddy current loss when the transformer is operated at 240 volt and 50 hertz. Okay, so that is the question here. So before that, so clearly you have to find the hysteresis loss and the eddy current loss. So we will take the voltages separately. So let this voltage V1 will be equal to 192 volt. Okay, so this is the answer, and the frequency F1 is equal to 40 hertz. Okay, and at this point the total iron loss, now don't take this as a hysteresis loss or eddy current loss separately. Okay, this is the total iron loss of the transformer. Wi2 will be equal to 39.2 watt, right? And V2 is equal to 288 volt, and the frequency F2 is equal to 60 hertz. Okay, and Wi2, this is Wi1. So Wi2 is equal to 73.82 watts. Okay, so this is the thing they have given here. And they are asking if V3 is equal to 240 volt and F3 is equal to 50 hertz. Okay, so they are asking what is the hysteresis loss WH3 and the eddy current loss WE3. So this is the question they are asking. So we have to indirectly find the case of the problem, in what case it is coming. So let us take each V1 by F ratio, V by F ratio. So in this case, the V by F ratio is 192 divided by 40. Right, this case 192 divided by 40. So this value is equal to how much? Let me just see the value. I think it is 4.8. Yeah, it is 4.8. For the second case, it is V by F ratio is 288 by 60. This is also equal to 4.8. And for the third case, V by F ratio is equal to 240 by 50. So this is also 4.8. Okay, so all the values are same. So the entire problem is coming under case 1 of the problem. Okay, so entire problem is coming under case 1. So here V by F is equal to constant. So we are having case 1. Okay, so in case 1, what is the thing that you know? In case 1, we know that WH is proportional to the frequency. Okay, that means I can write WH is equal to A into F. Okay, so I am using this using A and B method in this particular problem because that is a little bit easier for this. But you can use the other method also. What I told, you can take WH1 separately, WH2 separately, and divide those two to get the results. It's not a big deal. Okay. So and the eddy current loss. So the eddy current loss is proportional to F square, right? So we know that the eddy current loss WE is equal to B into F square. So these things we have derived बहुत पहले से ही. Okay. So we can find that so WH3, so we have to find WH3 and WE3, right? So WH3 is equal to A into F, so that is A into what? A into F3, right? So what is F3 value is equal to? F3 value is 50 hertz, so A into 50. Okay, and WE3 value will be equal to B into F3 square, right? E3 for 3, 3 for 3, 2 for 2, 1 for 1, it's like that. Okay. So this is B into 50 square, right? But we don't know the values of A and B. Okay, we don't know the values of A and B. For that, we can use the information which is given in this particular this thing here. Okay, we can find the information from this given information what is here. Okay, so first let us write WE1. So WE1 is nothing but WH1 plus WE1, right? This WI1, sorry, why I don't know, I'm always putting this as WI1. So WI1, that is the iron loss for the first case, this one is equal to hysteresis loss plus eddy current loss for the first case. Okay, so now WH1 value will be equal to A into F1, right? So A into F1, okay, plus the eddy current loss is equal to B into F1 square, right? That means the WI1 value, which is this is WI1, this is WI2. So the WI1 39.2 is equal to A into F1. What is F1 value? 40 hertz. A into 40 plus B into 40 square. Okay, B into 40 square. And WI2 is equal to WH2 plus WE2. Right? WH2 value will be equal to A into F2 plus WE2 value will be equal to B into F2 square. Why? Because this is all coming under case 1 of the problem. Okay. That means I can write this equations. So WI2 is how much? WI2 value is 73.2 watts. 73.2 is equal to A into, what is F2 value equal to? F2 value is given to be 60 hertz, right? So A into 60 plus B into 60 square. Okay. So if you solve these two equations, you will easily get that the A value is 0.5. Okay. And the B value is equal to 3 divided by 250. Again, I am telling, use your calculators and do all these problems. These are two equations with two variables, so you will get this value. So if you substitute these A and B values here, because A is a constant and B is also a constant, okay, a constant of proportionality. So it is valid anywhere. So if you substitute that value, WH3 will be equal to A is 0.5 into 50. So this will be equal to 25 watts. WH3 is 25 watts. WE3 is equal to B into F square. So 3 divided by 250 into 50 square. Okay. So this value will be 30 watts. Okay. So that means in this problem, WH3 is equal to 25 watts and WE3 is equal to 30 watts. Okay. So if you want, you can write the WI3 value will be equal to 25 plus 30 is equal to 55 watts. Okay. It is 50. So it is in between WI1 and WI2, because voltage and frequencies are also in an in-between value. Okay. So these are three important numericals. I hope that the concepts of the iron losses are getting more and more etched inside your mind. So if you have liked this video, please like, share and subscribe the channel, and do please recommend these videos with your friends or anybody who is interested in learning these topics or is having any difficulty in understanding these topics. Okay. So you know that sharing is caring, and you have to share the knowledge. Only then this channel can move forward in the way it is moving now. Okay, so till I see in the next video, it's me Varun signing off, and have a great day. Thank you.